everyone, welcome back to the channel Sampoorn Adhyan. I'm Pawan Gupta. Today I'm going to explain about the VI characteristics of SCR using only DC sources, and actually I will make a PSpice simulation video on it, and there you can actually utilize the DC sources to make the VI characteristics of SCR. In the next video I will explain it to you that how to work on the PSpice video. But here actually I have decided to introduce and tell about some theory part of VI characteristics of SCR, because it is beneficial for those students who are actually starting their studies for the power electronics subject from this semester and onwards. Previously they don't know about that what is the SCR and what is the SCR and its characteristics. So let's start with the PPT. Now, this is a silicon control rectifier. It is actually a 4-layer, 3-junction, 3-terminal device. You can see that here we have a P-type, N-type material, just similar to the diode, normal diodes, and there are 4 layers of a P-type, N-type materials, out of which the P-type material, then N-type material, and then again P-type material and N-type material is actually cascaded and or get together to make a SCR. Now there is a 3-terminal which you can see that anode is there, and in the upper P side material, and the lower N-type material there is a cathode, and there are 3 junctions J1, J2, J3 are there because 4 layers are there. So it is a 4-layer, 3-junction, 3-terminal device. Its symbolical diagram is represented like just similar to the diode. You can see that on the P side it is just similar to the diode. On the P side there is an anode, on the N side there is a cathode, and but there is a third terminal is noted near to the cathode side because it is actually provided on the P layer near to the cathode side. Also, one thing is that when you apply the forward positive and negative voltage at anode and cathode, then it has property to forward blocking the voltage, unlike the diodes. If it will become the like diode, if you take and it will become the forward bias, it will start conducting. As soon as the diode will become the reverse bias, it will start it will stop conducting. So actually unlike the diode, here the SCR also has the forward blocking capability as well as the reverse blocking capability. But why it is called as a power electronics device? Because here, unlike the diode, here we are actually using the semiconductor material, same type of a semiconductor materials, but their doping levels are changed so that it can withstand with the higher voltage and the current ratings. Okay, so it can carry the high current as comparison to the normal electronic devices, and it can withstand with the very high voltage as comparison to the normal electronic devices. So it can be like from some volt to hundred of volts to kilo of volts also, and it can carry the some ampere currents to the 100 and 1000 amperes of the current, depending upon what type of SCR you are choosing. So here I have listed out the few points. You can read it as a that is I have already told you it. Gate terminal is also connected to the P type layer near to the cathode terminal. We will come back to the gate terminal role little later. That further first of all I want to actually discuss about the positive and negative voltage applied at the SCR when you make the forward biasing of it. When you make the forward biasing of it, junction J1 will become the forward bias, junction J3 will become the forward bias, but the junction J2 will become the reverse bias. So when the junction J2 will become the reverse bias, still there is a positive voltage at anode, and cathode has a negative voltage. It is not allowed to flow the current from the anode to cathode. So to break this particular blocking of the SCR, actually we are applying some triggering methods. The triggering point is that point after which the SCR will start conducting, or the moment at which the SCR will start conducting from anode to cathode. So if we do not apply any gate voltage over here between the gate and cathode, so what we can see that if we keep on increasing from 0 to some high value of anode to cathode voltage, and we actually make it gradual change, so we will find that after a certain high voltage of the SCR, depending upon what is the rating of the SCR, you will find that there will be a avalanche breakdown occur across the junction J2, which is the reverse bias, and that avalanche breakdown is good enough to just break this particular blocking capability, and the anode to cathode conduction will start conducting. Okay, so it is the forward triggering method. You can see that here I have also listed the method of triggering. So you can see that the following methods can be used. The forward voltage triggering, when you actually applying the some high value of a voltage across the anode to cathode from, and you actually start increasing gradually 0 to some high value, and you will find after a certain value of the voltage it will start conducting, but it can damage your SCR also. Or the second method is the dv by dt triggering without applying the gate. If you like applying the anode to cathode voltage suddenly, if you applying there is an instantaneous change in the anode to cathode voltage, then again there will be your SCR is work as a capacitor across the junction J2, because junction J2 is having a depletion layer over here and both side there is a charge separation, so it behaves like a capacitor, and due to the sudden application of or sudden change of the anode to cathode voltage, there will be a high capacitor current which will actually allow the SCR to conduct. Again it is not desirable, because here again you are not controlling it, it is going to happen because of the sudden application of the anode to cathode high voltage. So it is called as a dv by dt triggering. Third method is a temperature triggering. Temperature triggering is that kind of a triggering, like if you apply a anode to cathode voltage, still it is in the forward blocking mode, there is a leakage current will flow, and that leakage current will actually create the some losses in the layers, and that losses will actually create the some temperature rise among the all these layers. And when the certain amount of leakage current will be there, and there is a continuous temperature rise in the layers, then there will be a free charge carriers will become into the action, and then it will also allow the anode to cathode conduction. So it is called the temperature triggering. So all the first three methods are undesirable method, because in this condition your SCR can damage and it is not in under control. You can also know that there is a third terminal, gate terminal is given over here. So we are going to talk about the gate triggering. You can see the fourth method is a gate triggering method. So what is exactly it is, when you apply a anode to cathode voltage, and if you are apply some gate and cathode voltage is also there, so small gate and cathode voltage will allow to flow the some small gate current in the third p layer, and that will actually inject some charge carriers in the third layer of the p type material, and that will going to come recombine with the junction J2 depletion layer, and that will reduce the depletion layer by the time, and the anode to cathode conduction can happen after a certain value of a charge carriers will move to the junction J2. So this is nothing but a kind of a controlled turning on method of a SCR. So it is very much desirable, and here we are not actually making any any kind of damage or any kind of harm to the SCR, because it's going to happen before the very well before the breakover voltage of the SCR. Now the fifth one is actually the light activated triggering. In spite of giving a gate terminal over here, if we provide the third layer with the light activated area here, and if we impart some light on it, so light photons always has the energy, it will impart the energy in the third layer, and that will make the some free charge carriers in the third layer, and that again will recombine with the depletion layer of the J2, and that will also work as a gate triggering, and this is called the light activated triggering. Okay, so the first three methods are actually undesirable, last two methods are the desirable, and it is a semi controlled device. Why it is called a semi controlled device? Because you can turn on the SCR by applying the gate voltage, but you cannot turn on the SCR by removing the gate voltage or by applying the negative gate voltage. So this is actually a semi controlled semiconductor device, and it can work as a controlled rectifier also in the different cases. When you study in the power electronics subject further, you will find that these things will be there. So now if we go further, then what are the actually circuit you required to experiment the VI characteristics of SCR in the lab? So this kind of a circuit you require, you can see that the anode, cathode and gate terminals are there, and you have to apply a DC source across the anode to cathode, and some load resistance R1 ohm over there, and also you can apply a voltmeter and a meter to measure the current, anode current, and as well as the anode to cathode voltage. Then again you can apply a DC source and some controlling resistance R2 ohm to control the gate current through the SCR, and you can again apply the voltmeter and a meter to measure the gate voltage applied to the SCR and the gate current provided to the SCR. So when you actually make this gate voltage 0, and if you keep on changing the value of the DC source from 0 to 30 volt. Why I have taken the 0 to 30 volt? Because in the most of the lab normal hardware labs of the colleges and the departments, you will find the 0 to 30 volt variation of the DC supply. Further, you can have a more than that of also, but it depends that what availability you have. So you can change the value from 0 to some voltage, high voltage of the SCR, sorry, as DC voltage, and you can see that without applying the gate voltage there will be a point occur after which the SCR will conduct, that is the breakover point. So the first case is like that, the forward voltage triggering, when you are actually observing the breakover voltage without applying the gate voltage, and this is you can achieve by varying the DC supply on from anode to cathode. Okay, now the second case is that if you again not applied the gate voltage, and you actually apply the negative voltage over here, and you actually increasing the negative voltage from 0 to some high value, then you can find that after a certain value again SCR will start conducting. That particular voltage is called the breakdown voltage. So that is actually belongs to the reverse voltage characteristics of SCR. So by this, without applying the gate voltage, you have the two cases: case 1 forward voltage triggering, and case 2 the reverse voltage triggering. Okay, so these two are all always undesirable. You don't want to damage your SCR, or don't want to allow the SCR to conduct without your permission. So actually the third case is that when you apply a certain gate voltage over here, and if you keep on changing the anode to cathode voltage, you will find that well before the breakover voltage, your SCR will start conducting, and your current will shift from the leakage current to the normal load current. So in this way actually you can apply the different gate voltage by the with the variation of the anode to cathode voltage, and you can note down the anode to cathode voltage and the anode current by voltmeter and ammeter readings, and you can plot the VI characteristics of SCR. That is called the gate triggering of a SCR. Okay, so this is nothing but the one glimpse of a VI characteristic of a SCR I have taken. The x-axis is the anode to cathode voltage, and the y-axis is a anode current. Now you can see that if you start increasing the voltage from 0 to high value without applying the gate voltage, if you see that Ig is 0, so that means your gate current is 0. So after a certain value of a breakover voltage, your SCR will shift from the turn off action to turn on action, and the current will start increasing from some high leakage value to high value. Okay, from this particular reason where the leakage current is there, that is called the forward blocking mode, and the current is known as a forward leakage current. Okay, now if you apply a certain negative voltage from 0 to high value, again there will be a reverse blocking mode. So there will be a reverse leakage current, and after a certain value of a reverse voltage, again your SCR will start conducting. So your current will suddenly go up to the high value, because your conduction will start after this point. So this is called the breakdown voltage, and the current corresponding to it a very high current. Okay, so again this is a reverse voltage triggering. Now what about the gate triggering? When you apply a certain gate currents, like here we have taken the Ig1 is greater than Ig2, Ig3, and then Ig0. So the if you keep on increasing the value, here you can see that it is Ig3 smaller value, Ig2 is a little bit higher value, and the Ig1 is a more higher value. So you can see that these corresponding to this Ig3, the turn on voltage of anode to cathode is well before the breakover voltage. So your SCR will turning on in the very safe conditions, and the characteristics is shifting from the leakage characteristics to the normal load current characteristics. Okay, so in this way that different gate currents can be provided, and you can vary the anode to cathode voltage to plot the anode current with the respect to anode to cathode voltage. Now the two currents are very important here, the latching current and the holding current. The latching current is that current beyond which the SCR is remain turned on if you still remove the gate voltage. So once the your SCR will be turned on, and if you remove the gate voltage, if the current is more than the latching current, it will be remain turned on unless your SCR current will go below the holding current. How it will goes to the holding current? Holding current is that current below which the SCR will stop conducting if there will be no application of the gate, also if there will be application of the gate. So if the in any case, like if you change the anode to cathode voltage, or if you change the load resistance in such a way that the anode current will go below the holding current, no matter whether there is a gate voltage is applied or not, so your SCR will go into the off condition. Okay, so the holding current is that current below which the SCR will become turn off, and the latching current is that current beyond which your SCR will remain turn on, and there will be no turning off action if you remove the gate voltage. What happened between the latching current and holding current? If like current is between the latching current and holding current, if you keep on applying the gate voltage, so it is still in on condition. If you remove the gate voltage at this instant, that when your current anode current is between the latching and holding current, and if you remove the gate voltage, then again your SCR will turn off, because there will be not good enough charges in the layer, so it will remain turn on. Okay, so these are the concepts are here related to the VI characteristics. So during the plot of the this one, we required the first quadrant and the third quadrant characteristics, and we actually looking for the some breakover voltage, and other turning on voltage with respect to the some current of a gate, and then we try to plot the anode current. We also looking for the breakdown voltage and the current and leakage current also. So these things you required for the VI characteristics of a SCR. Now these are the different type of SCR I have listed: plastic module, discrete plastic, press pack, and stud base. Depending upon their different application and voltage and current rating, you will find the different type of SCR in the market, and with the different model number, there is a lot of voltage and current ranges are available of SCR. It is not like that only this type of 4 SCR or 5 SCR is there. You will find a lot of variation in this. Okay, now these are the PSpice 2 and 1595 SCR. When you if you actually want to do the PSpice simulation, you will find in the library 9.1 version, you will find 2 and 1595 SCR. It's actually data sheet you can find on the Google. When you Google it, you will find the data sheet also, and its terminal are like here there is a notch, and if you go in the clockwise direction, you will find cathode, gate, anode. Okay, so these way you can actually determine the 2 and 1595 SCR, where in PSpice actually you don't require the hardware, but actually if you want to apply in the lab, then you require the hardware. So that's why I have included here, so that you can identify the SCR actually in the lab, and it is of a normal voltage rating. Here I have shown the maximum rating of this SCR, so you can see that the different ratings are given for 2 and 1595. There are also variation of 96, 97, 98, 99, but we are actually focusing on the 95 version because it is available in the PSpice 9.1 version. And so there is a peak reverse voltage is near about 50 volts, and the forward current RMS is 1.6 ampere, and similarly the other ratings of the gate and the temperature is also given. If you go for the electrical characteristics with the certain condition of 25 degrees Celsius, and the gate to cathode resistance, current control resistance is 1 kilo ohm, so you will find the peak forward blocking voltage is 2 and 1595 is near about 50. I will show you in the simulation, it will come around this one. And the peak reverse blocking current and peak forward blocking currents are also given the 1 milliampere. This TYP is nothing but the typical value and the maximum value and the minimum value, and different holding current and other things are, and great triggering currents are also given for this 2 and 1595 data sheet. You can download it and you can refer it. Now these are the kind of simulations we will find for the breakover voltage. If you apply the 0 to high voltage, you will find near about more than 50 volts it will start conducting without applying the gate. Again the second case, when you apply the reverse voltage, you can see that when your voltage is changing from 0 to negative voltage in this direction, you will find a breakover voltage over here, and the SCR will start conducting. Again, if you apply the gate voltage and if you change the anode to cathode voltage, you can apply change the voltage, and you can plot the current, and you will find this kind of a simulation result with the gate triggering method. Okay, so these kind of things you will find in the simulation. I will show you in the next video that how to simulate it. These are the observation tables you required. Like gate voltage, you have to get either gate voltage or gate current, you can note down over here. For a certain gate voltage or gate current like 0 or some value, you can plot the variation of the anode to cathode current, and anode to cathode voltage and anode current also. At the last, you have to conclude the things in the terms of the different points, that what holding current you have observed, what breakover voltage you have observed, what are the different gate currents, and corresponding turning on voltage you have observed in the SCRVI characteristics. So these things can be listed by the students during the experimenting it on the PSpice 9.0 version. So in this way, actually, like I'm looking for the VI characteristics of the SCR. In the next video, please look at that one to know that how to simulate it properly in the OrCAD PSpice 9.3 version, because it is a student-free version. You can avail it clearly in my playlist. I have also told that how to download, how to install, how to create the things, so you can actually refer those videos also. And please subscribe the channel and press the bell icon so that you can get the latest notification of the upcoming videos. Thank you. Hello.